Hi, everybody, and welcome back to General Science. Today, we're going to start off our chemistry talking by talking about atomic structure and what that is and kind of how it's changed over time. So, to get going, we'll start off by going all the way back to ancient Greece. And in ancient Greece, there were four major elements that the Greeks believed contributed to everything, and they were fire, earth, water, and air. And if you're like getting some major flashbacks there, those are the same elements from Avatar: The Last Airbender. So obviously they were onto something there. But it turns out that's not quite how things work. That there's more than just four elements. And the guy who really started to figure that out, or at least started giving us that idea, is Democritus. And he was a Greek philosopher, and he lived from about 460 to 370 BC. And he was the first person to come up with this idea of an atom. And he believed that all matter was composed of indivisible particles, which he called atoms. And he believed that there are different atoms that were different sizes and had different properties. And back then, when he first came out with this idea, the other philosophers around him were like, yeah, whatever, Democritus, like, sure, everything's made up of these small particles. Ha ha ha, that's hilarious. So they didn't quite believe him when he was talking about this. This wasn't something that was common knowledge, something that was accepted by the people of his time. Now, if we fast forward to the Middle Ages in Europe, there were people called alchemists, and they were kind of like the first chemists. And they wanted to use science and magic, right, to change substances to others. The major ones were, of course, tin to gold and water to wine. Now, these attempts never worked. Nothing they did ever actually changed anything, but they were trying. They were experimenting with stuff, trying to make some chemical changes. And that never really amounted to anything, but it was a good start for people to kind of get to this idea that maybe there's a chance that we can change one thing to something else if we do enough stuff to it. So then, kind of moving forward with that, there's a scientist called Lavoisier, and he was from France, and he experimented with combustion. So he basically just burned stuff in his house, and he kind of discovered oxygen as this element, and he determined that matter didn't disappear, and that it just changes forms or changes shapes. And this idea is going to come in handy later when we talk about some more complex science here. So now finally we're at the idea where we're finally starting to get all these ideas coming together. And the first guy to really kind of take those ideas and put them into some sort of model of what an atom might look like was John Dalton. And he was around from 1766 to 1844, so basically the first big chunk of American history. That's when John Dalton was alive. And he's considered the father of atomic theory, and the reason is because he's the first one to kind of cohesively unite some ideas about atoms. And they were super awesome ideas. And for the most part, his ideas are still something that scientists go off of. He was mostly correct. Now, some things were wrong, and things have been corrected over time, and he was like on the right hunch, but he didn't quite get there. But a lot of it, though, was spot on. And so that was pretty great. So he made a lot of really interesting thoughts and decisions and discoveries that, for his time was fantastic because they've stood up to all the testing we've done on them. So here is atomic theory, and he published this in 1803, and he gives 5 postulates, so 5 things that he thinks are true about atoms. The first one is all matter is composed of extremely small particles called atoms. So basically the first one is saying Democritus was right. All the way back then, we're all made of these indivisible particles. Okay. 2, he says all atoms of a given element are identical, and they have the same size and mass and chemical properties. So there are these new things called elements, and those elements have unique properties that only they have, as well as size and mass. He said all atoms of different elements are different. So these elements, right, they're different than each other. They can't be the same. They're clearly different things, right? They can't be made the same that way. 4, atoms cannot be created, divided into smaller particles, or destroyed. Now, this has been changed. We've since proved that you can separate, join, and rearrange all of these things, and so that does end up changing. But for at that point, that was a pretty solid estimate based off what he knew. And then finally, atoms can combine in definite whole number ratios to make compounds. And that basically just means that you can't take like half of an atom and attach it to something. You have to attach the whole atom. And that's still true, right? You can still only attach full elements to things. When you're making compounds, you can't take like half an atom and be like, we're going to put half a carbon on there. It doesn't work that way. So that was Dalton's atomic theory. And so based on those kind of 5 postulates, most scientists in the 1800s believed that an atom was basically just like a ball. All right, these tiny, tiny, tiny balls that we couldn't see. And yeah, so that was what they thought back in 1804, basically. It was that atoms are these balls that can't be broken apart. So indestructible balls. Okay. Dalton was also credited with 3 atomic laws that have been proven since his passing. The first one is the law of conservation of mass, which basically says that matter cannot be created or destroyed in a physical or chemical process. It's just transferred to some other thing, which kind of gets back to one of his postulates. The law of constant composition, which says that the ratio of atoms that form molecules are constant, right? So water is always going to be 2 hydrogens, 1 oxygen. It's never going to be any different than that. It's always going to be like that. And then he also did what's called the law of multiple proportions. So if 2 elements can combine to form more than 1 compound, then the ratio of the second element combined with the mass of the first element is always going to be a ratio of small whole numbers. And I've got some examples here. For example, carbon monoxide and carbon dioxide, right? Those are 2 different carbon-oxygen combinations, but those are going to be the least smallest ratio, right? Nitrogen and oxygen make a bunch of compounds as well, and they're always written as the smallest possible ratios. Those are all Dalton's ideas. Let's move on. Okay, so now the next person who really made some contributions to this atomic theory was J.J. Thomson, and he was around from 1856 to 1940, and he was doing a series of experiments to kind of learn more about these particles, and so he was using what's called the cathode ray tube to try to prove Dalton's model. And he was trying to prove that he could actually break the balls into smaller pieces. And Thomson is credited with discovering what's called an electron. So what's an electron? Well, that's in a second. First, you might not know what a cathode ray tube is. A cathode ray tube is basically like this big glass tube with some metal in it, and it's connected to a battery. And when power goes through it, it creates a color. Basically, a cathode is like the kind of tube that you would see in like those old school TVs. So if you ever threw out like a really old big box TV and you smashed it open, you'd find a bunch of these little tubes in it. And so basically what happened is he put this tube in a magnetic field, and he thought, oh, okay, so the stream was going to travel in a straight path. But instead, he found that the path curved away from the negatively charged plate and towards a positively charged plate. And that would be because electrons are particles that can be removed from atoms, and they're negatively charged. So in this experiment, Thomson concluded that there must be some negatively charged particle in atoms, and these electrons, which was what he called them, have to come from atoms. So that meant that the atoms had to be able to come apart because this negative particle was coming off of them. Okay, so now we have these electron things, and so Thomson is like, okay, so they can't just be this ball anymore. It has to be something different. And so he came up with what he called the plum pudding model, which is so British, it's not even funny. Plum pudding is gross. And no one can tell me differently because I've seen and tried it before and it was disgusting. But basically, the way the plum pudding model works is that there's this big kind of circle that you can imagine as like this pudding that's positively charged. And then the raisins in the plum pudding scattered about are these electrons. And so overall, the atom is neutral because the atom has the same amount of positive and negative charges. And in his experiment, he was able to strip some of those electric particles out of this pudding, basically, and that was how he discovered the electron. So that's what Thomson thought. So now the next person who comes along and starts working on this issue is Rutherford. And so he was around from 1871 to 1937, and he takes this plum pudding model and he's like, okay, I'm going to add to it. And so he uses a new experiment called the gold foil experiment, and he discovers the existence of the atomic nucleus and kind of gives way to the idea that there are these things called protons. So let's take a look at what this is. Basically, the gold foil experiment was he was going to take this big strip of gold foil and he was going to go bombard it with these new things they had just discovered called alpha particles, which are positive charges. And so he was going to take that and he was just going to shoot it at gold foil. And based off of the gold foil, or based off of previous experiments, he predicted that these positive charges would just go straight through the foil. So he had like a receptor around the other side, and he was expecting just to get, pings from these positive particles right behind the foil. So nothing was going to happen. It was just going to go straight through. But what happened is these positive particles got deflected back about 1% of the time. And that's because this positive charge was hitting a central mass of positive mass, right? And so it was getting hit off that and getting repelled or knocked to the side. So it wasn't all going straight through, because some of this positive charge was hitting another positive charge. So because of that experiment, he had to come up with a new model, because clearly he had broken the plum pudding model. And so this is kind of what he ended up coming up with. And this is kind of the basic level atomic theory that we go off of today. And it's that the atom has this positively charged nucleus. So kind of like a cell has a nucleus we talked about in biology. Atoms also have nucleuses, nuclei. They have nuclei. And this nucleus contains almost all the mass of the atom. Okay, so most of all this atom, right, all this space an atom takes up, the majority of its mass is in the center, and it's positive. Okay, and it occupies a very small volume, so tiny part of it. And then these negatively charged electrons are spinning around in the other volume of this atom. So the atom is mostly empty space, which is kind of hard for us to think about, right? If you take things that are solid and you're holding them, right? Like I've got this off-brand sports drink here, right? Kirkland, ooh, right? If you have this off-brand sports drink, right? You think of this as very solid, right? This space is being taken up by a solid thing. But in reality, the atoms at the microscopic level, the atomic level, are mostly empty space. And they're connected together through these series of charges. And that's what's making this solid object in front of me. Okay? So the atoms are actually not solid blocks. They're more like clouds with little dots in the center of them, which is kind of how I think about it. So now he called this the planetary model, which makes sense, right? From what they knew about planets, right? There's something at the center of our galaxy, right? In our case, it's the sun, and planets rotate around them. So he basically said the nucleus was like the sun of the atom, and the electrons were like planets rotating around this positive nucleus. Okay, and so he called it the atomic planetary model. And like I said, this is kind of like the basic general atomic model that we use to explain to kids and middle schoolers and basic high school level chemistry. So the general area we have. Now, after that, we knew a lot of this stuff was happening. This guy named Mendeleev, who was from Russia, he took all the known elements and he put them and organized them in a table based off of all the notes and things he had learned from all these different scientists. And he did such a good job making this table that he had places reserved in it for elements that had not actually been discovered yet. So there were elements that existed, and we didn't know about them yet, but he was like, based on what I see in these trends, there should be an element here, and I know that because of these trends, and he was right. So he predicted a bunch of elements that ended up being discovered much later. And you know what the periodic table looks like. If not, go to Google, search image search periodic table, one will pop up, so you can see it. And that's kind of how we've organized all these different types of atoms, because that's what elements are. They're just different types of atoms. So now going past the basic model, the next kind of guy to step into this atomic, kind of the atomic maelstrom of what an atom looks like was Niels Bohr. He was around from the 1880s until 1962, very influential scientist on multiple fields, but he did do some work on atomic theory. And he actually worked in Rutherford's lab. So he was one of Rutherford's students and one of Rutherford's colleagues. And he was wondering why these negative electrons aren't just attracted to this positive nucleus and like smash into it. And so he ends up actually disproving the planetary model. It doesn't quite work that way. Now, that's kind of our basic way of explaining it, but it's not exactly the way it works. So basically what he ended up doing was he used experiments with light and interacting it with matter, and he developed a new model based off of that. And his model is called the energy level model. And so basically it's just kind of like a tweak of the planetary model. And what happens is the electrons are actually arranged in these circles around the nucleus, and each circle has a different energy level. And so the electrons are in constant motion, traveling around in these circles at the speed of light. And if they get enough energy, the electrons can jump from one circle to the other. And that's basically the main change that was happening when Bohr was fixing this model. And they travel so fast that they can't actually get pulled into the nucleus. So that's his explanation for why these negatively charged particles don't just slam into the nucleus of an atom. It's because they're going so fast that the attraction can't pull it in because they're just going super quick. Okay, so he made some propositions that have for the most part been proven true. Right, protons and neutrons are in the nucleus. Neutrons, which I haven't talked about yet, are these extra masses in the nucleus that are neutrally charged. Electrons can only be certain distances from the nucleus, which we found out to be pretty true. The electron orbits in the nucleus are at fixed energy levels, which is very true. And the electrons must absorb or emit a fixed amounts of energy to travel between these energy levels. And that has also been chosen to be true. And we've got lots of data to support that, electrons can only emit certain levels of energy. And that actually is why certain things are the certain colors that they are, because of that certain energy that gets released. It's all about electron energy levels, which is pretty exciting. It's a whole nother video that we could do and talk about why color is the way it is. Okay, so to wrap it up here, that's our basic atomic theory that we're going to talk about, at least for this. There's obviously much more that we could go into because there's been lots of developments since then. And in actuality, I might have someone who knows way more about it come on the series and talk about it with me so that we can get a better understanding of things beyond the Bohr model, if you're curious. So if you are, you should like and subscribe. And continue watching General Science. We're going to talk about some more chemistry and then move on to our other major sciences. And we might have some guests popping in here and there to explain things in more detail than I can, because I'm not an expert in everything. I'm just one man. Anyway, thank you so much for watching. I hope you've enjoyed this episode of General Science. I'll see you next time.